Alright, in this video I want to go over the voltaic cell experiment and go over just a few things that weren't covered in the video. So in the experiment you'll remember that I took a solution of 1 molar zinc ions, and into that solution I placed a strip of zinc metal, and I also took a solution of 1 molar copper 2, and into that solution I placed a strip of copper metal, and then I connected the two solutions with a wire, and it went through a potential readout, and that potential readout was about a positive 1.10 volts only when the two half cells were connected with a salt bridge. And when one's drawing the diagram for, this is what's known as a voltaic cell, and it's called a voltaic cell because it produces current. Electrons flow in this direction from the zinc anode to the copper cathode. A voltaic cell, this flows spontaneously. And when you're doing this, you usually put the anode on the left and the cathode on the right. So I like to think of it as reduction as the cathode on the right. And then we can write the half reactions for this. You might remember over here we have an oxidation. So zinc solid goes to zinc 2 plus 2 electrons. And then over here we've got copper 2 plus 2 electrons goes to copper solid. And so for every zinc atom in the strip on the anode, let's just write anode over here for the place where the oxidation happens, and we're going to write cathode over here. For every zinc atom that gets oxidized, a little bit of this anode disintegrates because the zinc atoms go to zinc 2 plus and become dissolved. And then those 2 electrons, they travel through the circuit and they come over here to the cathode, and those 2 electrons react with some of the dissolved copper in solution, and that actually ended up getting deposited as copper metal on the cathode. So as this runs over time, the anode decreases in mass and the cathode increases in mass. And you might remember, as these electrons travel over here, there's got to be a balance of charge. Otherwise, you get a bunch of negative charge build up over here. Well, I should put it here like this. And a bunch of positive charge build up over here because this is losing electrons. And if that happens, the electrons aren't going to continue to travel because, it's going to get repelled by the negative and attracted by the positive. So that's why this salt bridge is necessary, because for every electron that flows this way, you can get a chloride ion traveling in this direction. Or, to balance the negative charge that's going in this direction, you can have a sodium ion traveling toward the cathode. Now let's look at the reduction potentials for these. We have copper 2 plus 2 electrons going to copper solid. That's a positive 0.34 volts, so I can write that over here. Yep. And here we have an oxidation. So we're going to flip this reaction, right? Zinc solid going in this direction to zinc ion. So that's got to be, since it's an oxidation, we're going to flip this, positive 0.76 volts on this side, and we add them together to get our 1.10 volts. Now there is a shorthand notation that is used to designate this whole voltaic cell, this whole electrochemical cell. And it'll be written like this. It's a shorthand way of doing things. We can say zinc solid. That's going to be zinc solid as our anode. And then there's a phase boundary, because this is a solid, and then there's a solution of zinc, 2 plus aqueous. That's in connection with the anode. And then there's a salt bridge, which is designated by 2 slashes like this. And then the the salt bridge connects us to the copper 2 plus solution. And then there's a phase boundary because this is liquid and this is solid, and then our solid copper. And the conditions for the solutions are usually listed. So 1 molar here and 1 molar here. So you'll sometimes see this listed as a shorthand way of designating this whole process that you see laid out here, or the experiment that I showed in a previous video.